Hey everyone, Ricardo here, and in this video I'm going to be showing you how to set up a Synchronism Check element using the SEL-411L protective relay. So a Synchronism Check element, or just simply known as a Sync Check element, is a protection function that prevents closing of circuit breakers when the magnitude, phase angle, or frequency across the breaker is significantly mismatched. Now we can use the output of this protection function to supervise closing of the circuit breaker in the logic of the relay, which is what we're going to be talking about in this video. And we want to do this, of course, because closing a breaker out of synchronism can have a substantial effect in the power system, and in the worst cases cause equipment damage due to excessive short circuit current. Now, before we go deeper into how to set up the Synchronism Check element in the SEL-411L relay, make sure to subscribe to our channel. We always post videos here about power engineering and power system protection and control. And if you want to learn more about power system protection and control, check out our online courses, where we go into these topics in a lot more detail. I'll leave a link to those courses in the description below. All right, so let's jump right into it. Let's see how we can set up the Synchronism Check element using the SEL-411L protective relay. So let's say, for example, that we have a 230 kV substation that looks like this, where we have a double bus, double breaker arrangement. And for this example, we'll assume that the line voltage is connected to the Y terminal of the relay. So this over here would be the Y terminal, meaning it's going to be the VAY, VBY, and VCY connections on the relay. And as you can see over here, that's a three-phase connection. And we also have the PT ratio over here, which is 2000 to 1, which is typical for a 230 kV line. Now we'll also assume that the bus voltages are connected to the Z terminals of the relay. In this case, the relay is implemented, again, in a double bus, double breaker configuration, so we can set it up to check for synchronism across both CB1 and CB2, so the two breakers that we have over here. So in other words, we can implement two sync check elements, one for each breaker. Now we'll assume that the bus 1 single phase PT connection is wired to the A phase on that bus. So this PT would be wired to the A phase, and that's going to be fed to the VAZ input on the relay. Now, just like that, the bus 2 single phase PT connection is also wired to the A phase on bus 2, and bus 2 over here is this bus on the right, and bus 1 is this one over here. So this connection is also for A phase, and the secondary of that PT is wired to the VBZ connection of the relay. And again, those two are single phase connections. Now, this is where things get a little bit complicated when we talk about the sync check element, because we could wire any of the three phases from bus 1 to the VAZ input of the relay, and the same is true for bus 2 as well. So we could wire B phase or C phase, or we can even wire the phase-to-phase voltages. So again, we have the three-phase connection from the line, that's this one over here, and we're going to use that as our reference so that we can compare the bus side voltages, but the bus side voltage that we use can be any one of the phases, or it could even be a phase-to-phase voltage. It doesn't have to be A phase. It's just that for this example, to keep things simple, we're going to use A phase, and we're also going to use the A phase for the line side voltage as the sync check voltage for the line side. Now in this case, for the bus side PTs, I'm assuming that we have Y connected PTs, and that's of course again because we're using the single phase A phase to ground voltage for both sides. So all three PTs are going to be Y connected. Now, as I mentioned, this is a 230 kV transmission line, which means that if we have 2000 to 1 PT ratios for all of our PTs, the secondary voltages are going to be 115 volts line to line on the Y terminal and 66.4 volts line to neutral on the Z terminals. And of course, 115 line to line equates to 66.4 volts line to neutral. So it's the same ratio for all of the three PTs, but again, we have a three-phase connection for the line side and single-phase connections for the bus sides. Now, let me actually jump into a blackboard, and what I want to show you over here is that, again, what we're doing with this sync check element is we're making sure that the phase angle, magnitude, and frequency on both sides of each breaker are within a specified range prior to closing the breaker. Now, these are, of course, not going to be exactly zero, but we should allow only a small mismatch between the two voltages before we allow a close. So for example, if our line side voltage VAY is over here, we want our bus side voltage to be somewhere close to that. It doesn't have to be exactly the same, but it has to be fairly close to it. So let's say, for example, this could be something like 5 degrees. We would allow a close in that case. Now, if the voltages were very far apart, so if you had VAY somewhere around here, but VAZ, the bus side voltage, somewhere around here, so 90 degrees apart, we of course wouldn't want to allow a close under those conditions. And again, the main point that I'm trying to make here is that the mismatch is never going to be exactly 0, but it should be fairly small. And we can set the tolerances that we're going to allow in the settings, as we're going to see here in a second. So let's jump into the settings file and let's see how we can do that. All right, so what I have over here are just default settings for an SEL-411L relay. And in here, of course, I'm going to be focusing on the sync check element. But of course, if you were to implement these settings for a real-life application, you would need to program all the other settings. Just know that for this example, we're just going to focus on the sync check settings. All right, so the first thing that we need to do, of course, is to start with the basic settings, the PT ratio and the nominal voltage. And we saw before, again, that we have 2001 PTs on both the line side and the bus side. And on the bus sides, we have that ratio for both buses. And we also assume that the line side PTs are wired into the Y terminal of the relay and the bus side PTs are wired into the Z terminal of the relay. And so to set the PT ratios and the nominal voltages, we can go to group 1, set 1, and line configuration. And in here, we see the PT ratio for both the Y terminal and the Z terminal. And the default in this case is 2001, which is the same for our example. So these settings are 2001. Of course, you will need to change these if you had a different PT ratio. Now, if we have a 230 kV transmission line, if we divide 230,000 by 2000, we get that the secondary voltage is 115 volts line to line. So that's going to be the nominal voltage for both the Y terminal and the Z terminal. Again, that's the line-to-line voltage, not the line-to-neutral voltage. That's going to be important when we get to the sync check settings. All right, then we need to enable the sync check function, so we can go to relay configuration over here. And this is where you set your enables. So basically all the elements that you're going to be using in your settings. We can scroll down over here to the sync check element, and that's over here. And we can see that we have breaker 1, breaker 2. For this example, I'm just going to focus on one breaker. So we're going to say that we're going to implement the sync check element on the bus 1 breaker. So I'm just going to enable one breaker. But again, just know that if you were to implement this for both breakers, you would of course need to set both sync check elements. So I can set this to yes, but notice over here that we also have Y1 and Y2 options. So let's enable this element, but let's also go to the instruction manual to see what Y1 and Y2 stands for and what's the difference between setting this element to Y, so yes, or yes1 or yes2. So let's go to the instruction manual, and here I have the instruction manual for the SEL-411L, and if we go to page 485, we're going to see the logic for enabling the sync check element. So this is the internal enable logic, which is this relay word bit over here, 25, 25, EN, BK, M, and then M stands for 1 or 2, meaning breakers 1 or 2. So this is the enable for the sync check element internally in the relay. Now again, we can see over here that we have basically 3 options given by these 3 AND gates over here. And you can see that which one of those options we use depends on the setting that we just talked about, E25, BK1. So we can set that to Y, Y1, or Y2. Now, if we set this element to Y, the relay makes sure that both the line side and the bus side voltages are within a healthy window, which we can of course set in the settings file, and we're going to set those to be some percentage above or below the nominal voltage. So in this case, 59 VP1 signifies that the voltage VP, which is the line side voltage in our case, is within a healthy window. And then we have the sync voltage 59 VS1, which is going to be the bus side voltage for breaker number 1. So those two, as you can see over here, have to be within a healthy window. And we're going to see here in a second how we define that healthy window. Now, if you set the enable to Y1, so this second AND gate that we have over here, What that means is that the relay is only looking at the difference between the line side and the bus side voltages and making sure that that difference is not greater than a certain threshold. So you can see over here that we have a different word bit, 59V-diff1. That's going to be the difference between the bus side and the line side voltages. So in this case, the relay only looks at the difference between the two, but it doesn't check to make sure that it's within a certain window. So for example, if both voltages were at 50% or nominal, then this would be a logical one at the output of this AND gate, and the sync check element will be enabled, even though the voltages are well below nominal voltage. And then if we set the enable to Y2, that's sort of a combination of both Y and Y1. As you can see over here, we have this portion, which is the same as just setting that enable to Y. And we also have this portion over here, which is similar to Y1. So what this means is that the voltages must be in a band that we define with the settings and also be within a certain range of each other. So the difference between the two voltages cannot exceed another setting. So again, it's just sort of a combination of Y and Y1. For this example, we're just going to use the Y option. Now, I mentioned before that here on the top, we see healthy voltage for VP and VS1, but what does that actually mean? What's the range that we would consider healthy? To see that, let's go to page 484. So that's shown over here in this graph. So again, what we define as healthy voltage is a band that we set within the settings file, and we usually set that around the nominal voltage. For our case, we're going to set that to be plus or minus 10% of the nominal voltage. Now, this is why I mentioned before that it's important that we also calculate the phase to neutral voltage, because again, we're comparing the A phase to neutral voltage from the line side to the A phase to neutral voltage from the bus side. Both of those are phase to neutral voltage, not face to face voltages. So again, if we have a 230 kV nominal transmission line, that voltage is line to line. We can divide that by 2000. That gives us that the nominal voltage in the secondary of the PTs line to line is 115. Now we have to divide that, of course, by square root of 3 to get the line to neutral voltage. And that gives us that the nominal line to neutral voltage is 66.4 volts line to neutral. So then we can set this band with these settings, 25 VH and 25 VL, to be plus or minus 10%. So we can say I'm going to set my lower end of that window to be 0.9 times 66.4. That gives me 59.8. So for our case, this is going to be 59.8. And I can set the top side of that band to be 10% above the nominal voltage. So 1.1 times 66.4 is 73.0. And that matches this. I'm just going to add the decimal point. So again, when we say that the line side voltage is healthy, we've defined that to be when the phase to neutral on the A phase is within 59.8 volts and 73 volts. That's plus or minus 10% of the nominal voltage. And we're going to do the same thing for the bus side voltage. All right, so let's go back to the settings file. And in here, we can go to the sync check function to set those bands. So we can go over here. Let me just expand this. We're going to go over here to Synchronism Check elements. Let me expand that. And we first have to define the reference. This is going to be what we're going to compare our bus side voltages to. In our case, it's the line side A phase voltage, which, as I mentioned, is wired to the VAY input of the relay. So the default setting is just fine. In this case, VAY. But again, if you're using another reference, you will need to make sure that this setting is set properly. So I'm going to leave that at VAY, and then these are the thresholds that I was talking about. So the voltage window low threshold, we said that that's 0.9 of the nominal voltage. In our case, that's 59.8. The voltage window high threshold is going to be 73.0 for our case. That's 10% above the nominal voltage. Now we can go here to breaker 1 synchronism check. So now that we've defined a reference, we also need to set the sync check settings for the bus 1 side. So let me scroll down over here, and that's down here under synchronism source. And again, here I said that the bus side voltage for bus 1 is connected to the VAZ input of the relay. So that's why we can use the default setting over here, which is VAZ. You will need to change that if you were using a different signal for the breaker number 1. So if you were using the B phase, for example, as your connection for that side, you will need to set this to VBC. It just depends on where you'll wire the single phase input from the bus side to in the relay. In this case, again, I said that the bus 1 side, we connected that to the VAZ input of the relay, and the bus 2 bus side voltage, we connected that to VBC. Since this element is for breaker number 1, we can set this to VAZ. Now we also have 2 more settings over here, which are for magnitude and phase angle compensation. And since we are using the phase to neutral voltages of A phase for both the reference voltage and the synchronizing voltage, we do not need to use them in our case. So we can leave that at 1 and 0. But let's actually go through an example just to see how you will use those settings if you had a different synchronizing voltage than you did for the reference voltage. So let me go to the blackboard over here. And again, this is a separate example, not for our example, but I just want to show you how you would use this if you had another voltage for your synchronizing voltage. So for example, if instead of using the A phase voltage from the bus side of breaker number 1, we were using the B phase voltage, then we would need to tell the relay, of course, that it needs to compensate for the phase angle difference because it would be comparing A phase from the line side. So let's say that VAY, which is the A phase from the line side, it would be comparing that to the B phase from the bus side. So that would be at minus 120 degrees over here. And again, this would be wired to VAZ, but it's actually the B phase bus side voltage. And so you need to tell the relay, compensate for this difference because you're not comparing apples to apples. You're comparing A phase from the line side to B phase from the bus side. So you need to shift or compensate for the phase shift of the B phase so that you can compare it to the A phase on the other side. That's what that setting is for, KS1A. Now I mentioned before that the synchronizing voltage doesn't have to be single phase, it could also be phase to phase. So for example, if we were using the B to C voltage from the bus side and we wanted to compare that to the A phase on the line side, we would need to compensate for both the phase shift and the magnitude difference because of course the phase to phase voltage nominally is going to be square root of 3 higher than the phase to neutral voltage. So we would also need to compensate for the magnitude. Now, like I said, in our case, because we're using the A phase from both the line side and the bus side, we can just simply leave the ratio factor, which is basically just the magnitude compensation, to 1, because we would expect the magnitudes to be the same on both sides since they're both phase to neutral. And the angle shift, we can also leave that to 0 because we're comparing A phase to A phase. So there's no need to shift the angles of one with respect to the other. They should be in phase theoretically. And just as a side note, this is why I said earlier that to keep things simple, you could wire the same phase from both sides of the breaker. All right, so we can leave those at default, 1.0 and 0. And let's scroll down here to the rest of the settings. So here we have a setting that's called the slip frequency or the maximum slip frequency allowed. What slip frequency means is the difference in the frequencies between both sides of the breaker. So one side might have a different frequency than the other, which means that the phase angle difference is not going to be static. They're going to be changing with time. Now the relay can compensate for this phase angle difference and the change in those phase angles, and it can account for the time that it takes for the breaker to close after we've issued the close signal. So in other words, the phase angles would be shifting with respect to each other. So if you keep one fixed, the other one is kind of rotating around it. The relay can compensate for that rotation so that it issues the sync check signal, accounting for the time that it's going to take for the breaker to close, so that at the moment that the breaker closes, the two voltages are actually in synchronism. Now, in order to do that, of course, we need to know how long the breaker takes to close. That's what this setting is over here. I'm going to leave those two to default. We're allowing a maximum slip frequency of 0.05 hertz. And we're saying that the close time is 8 cycles, which is typical for a breaker. But of course, you need to take a look at the nameplate for your specific breaker and see how long it takes to close, and then enter that setting over here. And then lastly, we have the maximum angle differences, angle 1 and angle 2. Typically, we would set the setting ang1 bk1, this one over here, for sync check and auto reclosing the circuit breaker. So for automatic closing of the breaker. And we would set the ang2 bk1 setting for when we're manually closing the breaker. And typically you would allow a higher phase angle difference when closing the breaker manually than when issuing an automatic closing signal. So we could, for example, set our angle 1 to 20 degrees and our angle 2 to 30 degrees. All right, so we have programmed all the settings for the sync check function. Now to summarize this a little bit, let's go back to the one line. And so here we said that we're comparing the line side A phase voltage, which is what we're calling the reference, and we're comparing that to the A phase to neutral voltage from the bus side. And for the relay to declare the two voltages to be in synchronism, they have to be within the band that we define in the settings. Again, that's basically this over here. We have to be within this band, and we define that to be plus or minus 10% of the nominal voltage, which in our case is 66.4 volts. So that band is going to be from 59.8 volts up to 73 volts. And then the relay takes measurements of the frequencies as well, and we're allowing a close if that difference is not greater than 0.05 hertz. And we're also saying that the angle difference at the moment the breaker closes cannot be greater than 20 degrees when we're doing an auto reclose, or 30 degrees when we're doing a manual close. Now the output of the sync check logic is relay war bit 25A1 BK1, and this is of course for breaker number 1, and this takes into account the time it takes for the breaker to close if the frequencies are slipping, so that we look at the angle difference at the moment the breaker closes, not at the moment when the close signal is issued. And again, the relay knows that because it knows what the maximum slip frequency is, and it knows what the closing time of the breaker is. Now we would then program this relay word bit 25A1 BK1 to supervise closing of the breaker. Now we can do that in a couple of ways. Some common ways to do that is to include that in the close logic of the output contact that issues the close to the breaker itself, or we could just map that relay word bit directly into an output and then wire that output in series with the closed coil of the breaker, so that we only allow the closing signals to go through when we're in synchronism. Of course, if we did that, we also would need to allow a close when the bus side is energized and the line side is de-energized. This relay word bit 25A1 BK1 only works when both sides are live and you're checking for synchronism. If one side is live and the other one's dead, this wouldn't assert. So you would also need to include logic that accounts for that case, because of course you do want to close if, let's say, the bus side is energized and the line side is de-energized. All right, so that's how you set up a synchronism check element using the SEL-411L protective relay. And if you want to learn more about power system protection and control, check out our online courses where we go into these topics in a lot more detail. We have courses on transformer protection, bus differential protection, and protective relay logic, just to name a few. And as always, make sure to like the video if you found it helpful, and subscribe to the channel for more videos about power engineering and power system protection and control. And we'll see you in the next one.